In this video, we're going to go through properties due to intermolecular forces. The essential question that we're going to answer is, how do intermolecular forces determine the physical properties of substances? The key point that I want to make is if you have multiple intermolecular forces acting on a molecule, the strongest intermolecular force is going to determine its properties. So let's talk about some properties. The first two that we're going to talk about are boiling point and heat of vaporization. So we've all done this before, or perhaps you've seen this before. You have a pot of water on your stove. And if you start to boil that water, that liquid turns into gas. You can see it escaping from the pot. Now, when you're boiling something, you're not breaking it apart. So if you have water, for example, you're not breaking it apart into hydrogen and oxygen. That's a really bad thing because you have an open flame and both are extremely flammable. Instead of breaking them apart into their respective atoms, you are separating them. So the water molecules are moving apart. But we know that when you have water molecules, there's an attraction going on because they both have hydrogen bonding. So you have to overcome that intermolecular force, that attraction that's going on between those molecules. We have to overcome that hydrogen bonding that's occurring. So when you have something that's boiling, you're just overcoming intermolecular forces. You're moving those molecules further apart. If you have stronger intermolecular forces, it takes more energy to separate those molecules. Therefore, you're going to have a higher boiling point. Heat of vaporization is the amount of energy it takes to change something from the liquid state to the gas state. So, therefore, if you have a higher boiling point, you're going to need more energy for it to move from the liquid state to the gas state. And therefore, you're going to have a higher heat of vaporization. All right, the next two properties that we're going to talk about are evaporation and surface tension. So evaporation, we've seen before. Maybe you've spilled a liquid and you've just left it out, and over time, that liquid will eventually evaporate. It'll disappear. If something has strong intermolecular forces, it's going to take more time for it to evaporate because, again, those molecules are being held tightly together. If something has a weak intermolecular force, it's going to evaporate very quick. And perhaps you've seen this before. If you've spilled something, alcohols do this. They will evaporate rather quickly compared to something like water. The last property that we're going to talk about is cohesion or surface tension. So this one, perhaps you've seen before if you've ever held a container of vegetable oil, or motor oil is another great one. Both of those liquids are very viscous. They move very slowly. If you take the container and you invert it, you'll see a bubble go from the bottom of the container to the top, but it moves very slowly compared to something else, like a water bottle, for example. If you invert it, the bubble inside the container moves pretty quick. If something has stronger intermolecular forces, it's going to have a higher resistance to moving, and therefore it will have a greater surface tension. All right, so let's do some examples where we're going to be looking at the molecules themselves. We're going to be predicting or determining the intermolecular forces present, and then we'll talk about some properties. So let's start with CH4 and H2O. So if we draw the Lewis structures for CH4, our Lewis structure is going to look like this. And for H2O, which we've done this one a couple times in previous videos, looks like that. Okay. If you don't know how to draw Lewis structures, you should definitely go back and watch my video where we go through how to draw these structures. All right, let's determine the polarity of each molecule. So CH4, everything attached to our central atom is the same, so it is going to be nonpolar. For H2O, we have two lone pair on our central atom, so this is going to be polar. All right, let's determine all of our intermolecular forces that are present. So for our nonpolar molecule, LDF is the only intermolecular force that's going to be present. For our water, it's polar, so we're going to have LDF, and we will also have dipole-dipole. We also want to look for hydrogen bonding. And remember, hydrogen bonding, you're looking for HF, HO, or HN. And we have two of those right here. So I have two HO bonds, so we have hydrogen bonding here. Now, hydrogen bonding of the three is the strongest intermolecular force. So if I'm comparing CH4 and H2O, our H2O molecules are going to have stronger intermolecular forces than our CH4s because they have hydrogen bonding. Because it has stronger intermolecular forces, it will therefore have a higher melting point than CH4. All right, let's go through another one. So we have CCl4, so carbon tetrachloride, and HCl, which is hydrochloric acid. Let's draw the Lewis structures. So for the first one, CCl4, carbon tetrachloride, it is going to look like this. Each chlorine is going to get 6 dots, 6 valence electrons, 6 electrons that are unbonded, and then they're going to be bonded to our carbon. For HCl, it will look like this. All right. Let's go through and look at each molecule and determine polarity now. So for our first molecule, we have everything attached to the central atom being the same. It is nonpolar. HCl, we have 2 different atoms that are attached, therefore it is going to be polar. All right, intermolecular forces. Our first one, our carbon tetrachloride, is nonpolar, therefore we'll only have LDF. HCl, hydrochloric acid, is polar, so it will have LDF. And it will also have dipole-dipole. Do we have one of the bonds needed for hydrogen bonding? The answer is no. So we are going to stop here. And the question says, which molecule will evaporate first, and explain why? Well, our carbon tetrachloride is going to evaporate first because it has weaker intermolecular forces. So it's going to evaporate first. All right. Let's go down to the next one. Oh, look, it's carbon tetrachloride again. So that'll be an easy Lewis structure to draw. And then we also have dicarbon. 6 is hexafluoride. So let's draw this one out. So there's our first one. And then C2F6, dicarbon hexafluoride. So 2 carbon atoms are going to go in the center, and then I have 6 fluorines that are going to be around. So just give me a moment while I draw those out. Again, if you don't know how to draw Lewis structures, you should go back and watch my video where I go through the process. I'm just kind of speeding through this because I've done these before. All right. Let's determine the polarity. So in both cases, they are nonpolar. So both have carbon as the central atom, and everything attached to our central atoms are the same. Therefore, it is going to be nonpolar. Both will only have, why my screen keeps tripping here. Both have LDF, as the only intermolecular force because they're nonpolar. So it says determine which molecule will have a higher surface tension and explain why. All right, so here we have two molecules that have London dispersion as the intermolecular force. So which one has the greater intermolecular force? And the answer is the larger molecule will have greater intermolecular forces. Therefore, our dicarbon hexafluoride will, and it will have a higher surface tension because we know the molecule with the greater intermolecular forces will have the highest surface tension. All right, last one. Let's draw these Lewis structures out. We have NH3, so nitrogen trihydride, and then we have dihydride dioxide, aka hydrogen peroxide. Let's draw the Lewis structures. So for NH3, oops, let's try to be consistent with our colors here. Nitrogen goes in the middle. We got hydrogen, 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 and you will have a lone pair of electrons on your nitrogen. For H2O2, hydrogens can't go in the middle, so we got to put our oxygens in the middle. You will have two sets of lone pair on each oxygen like that. All right. Both of these are going to be polar. The reason the first one's polar is because we have a lone pair of electrons on the central atom. The reason the second one is polar is because on our central atoms we have lone pair. So both will be polar. So intermolecular forces that both will have are going to be LDF. Just kind of put this in the middle because they're the same. So they'll have LDF, dipole, dipole. All right, and then do we have one of the bonds needed for hydrogen bonding? Well, for NH3, we have 1, 2, 3 of those. For our H2O2, let's see, we have 1, 2. So we go off of which molecule has the greater number of hydrogen bonding sites. So both molecules have a total of 4 atoms present. So for the NH3, you've got 4 atoms. You have 1 nitrogen, 3 hydrogens. For our second molecule, our H2O2, we also have 4 atoms. But our NH3 has more hydrogen bonding sites. It has more hydrogen bonds, hydrogen-nitrogen bonds, than the other one has hydrogen-oxygen bonds. So therefore, NH3 has higher intermolecular forces and will therefore have a higher heat of vaporization. And those are properties due to intermolecular forces.